Hey folks, we're in class number 47. Our goal is to quantify the change in force of gravity when changing mass and distance. And we want to calculate the force of gravity between two objects and identify gravity as solely an attractive force. So this question here, really similar to what we spoke about last class. We have force of gravity on the y-axis, distance on the x. So we know that as distance gets bigger, force of gravity has to get smaller. So we should be able to eliminate choices 1 and 2 immediately without thinking about it. Now we have a choice of these two here. Well, hopefully you recall that from last class, Fg is equal to G m1 m2 over r squared. Notice that r and Fg have an inverse square relationship. An inverse relationship looks like this. This relationship up here, number 3, that is a negative linear relationship. Okay, that would be like if it was negative r in the numerator. All right, now this next one's a little bit tougher. This is a tough question, so let's take it slowly. So read the question carefully. So we'll call this object 2. Okay, we'll call that object 2, just so we can differentiate the two. And we'll call this object 1. So let's compare object 2 to object 1. First, let's look at their masses. How do their masses compare? Hopefully you notice that object 2 has 2 times the mass of object 1. Let's see what else we know. Let's look at their distances. So how far is object 2 from the center of the moon versus object 1? Well, object 1, this is 1 radius, and this here is 2 radii. So object 2 it has 2 times the r as object 1. It's twice as far from the center of the moon. So let's see. When we double the mass, we know that we double the force of gravity. So this is 2 times the force of gravity. And when we double the distance, we have 1/4 the force of gravity. This is the same as the question we answered at the end of last class. So 2 times 1/4, we should get 1/2 the force of gravity. So we're going to look at some methods today in order to figure this out. They are a little bit more streamlined than this, in my opinion, but it's really important to emphasize that we are not calculating the force of gravity. We are simply looking at how it changes, how changing distance and mass change the force of gravity. We're not calculating the force of gravity here. So number 1 says, what happens to the force of gravity between two objects if you double the distance between them and half the mass of one of them? So how do we do this? So how do we get this qualitative, or it's quantitative, but we're not actually calculating the force of gravity. We just want to see how much it changes by. Is it half as strong, twice as strong? What's going on? So the first thing you have to do is write the universal law of gravitation. There it is. Then you're going to replace each variable with the factor you are changing it by. If it doesn't change, replace it with a 1. Okay, so we are doubling the distance and halving the mass of one of them. So let's see how we can go about doing that. Well, okay, I'm not changing little g or big G. Okay, I'm not changing big G, so I replace it with a 1. Big G is not equal to 1. I'm simply saying it doesn't change. Now let's look at the masses. Well, I'm definitely changing one of the masses. It's 1/2 of what it was before, so you replace it with a 1/2. The other mass doesn't change, so we're going to leave it as a 1. It doesn't matter which mass you do. Okay, 1 times 1/2 is the same as 1/2 times 1. And the distance between them is doubled, so I replace that with a 2. Again, these are not the actual values of any of these variables. It's not the actual mass, not the actual distance. I'm simply saying how much it is changing by. So I have 1 times 1/2 times 1 is 1/2 over 4, and that's 1/8. So my force of gravity is not 1/8 of a Newton. It's 1/8 of what it was before I made any of these changes. So I can write 1/8 Fg, Fg over 8, or 1/8 is strong, anything like that will suffice. The next one says the force of gravity between two objects if the distance between them is doubled. That's the only change. Everything else stays the same. So this one's actually a little bit easier. So big G ain't changing, nor are either of the masses. So those are all 1s. Again, those values are not equal to 1. Simply saying they're not changing because 1 times anything is 1. And r squared, let's see, I think you plug in a 2 there because we're doubling it, and we get 1/4. So you get 1/4 of f, or f over 4. Anything like that's fine. Now, number 3 was very open-ended. Basically, I don't want you to put any real numbers in or try to figure out the masses or the distances. I'm basically telling you that the force of gravity is 100 newtons. We're going to change something. I'm not going to tell you what. And now the force is 400 newtons. So it got 4 times as strong. I just wanted you to make up 2 ways to do this. You could have done a million different things. So one idea someone had was we can double each mass. What would that look like? Well, I'm not changing g, but I'm doubling each mass. So I replace those with 2's. Doesn't mention changing the distance, so I'll place that with a 1. 1 squared, so we have 4. Perfect. That's what I wanted. What if we could quadruple each and double the distance? So there's a lot going on there. So we're going to keep that the same. G doesn't change. We're going to quadruple each mass and double the distance. That's 2 squared. And I think that comes out to, let's see, 1 times 4 is 4. 4 times 4 is 16. 16 divided by 4 is 4. So that checks out too. What if we cut the distance in half? This one's a little bit tougher. Always working with the denominator is tough, especially when it's a fraction. So 1, 1, 1, because nothing up top changes, but the distance is half of what it was. Don't forget to square it, and that comes out to be 4 as well. Okay, because 1 over 1/4 is 4. So many different answers. So we spoke about the Cavendish experiment. Henry Cavendish is the one who figured out and quantified big G. These are the units for big G. It is on your reference table. Newtons times meters squared per kilogram squared. Those are just the units. You don't plug anything into those. They're just the units. Okay? So let's try using this equation and big G to quantify the force of gravity. So what is the force of gravity? So M1 is 90 kilograms, M2 is 90 kilograms because each student is a different mass, or an independent mass, but they are equal to each other. R is the distance between them. It's 3. It's not 1.5. It's the distance between them, 3 meters. And big G is 6.67 times 10 to the negative 11 newtons times a meter squared per kilogram squared. Again, just the units there. Now, very important, write the givens with units. Then write the equation in its standard form without anything plugged in. Okay, take your time. Now, you do not need to put in the units when you substitute. I'm doing it here just to show you how the units work out, but you do not need to. So 6.67 times 10 to the negative 11 newtons times meter squared per kilogram squared. The kilogram squared cancels with each of the kilograms here. And the meters down here, which is squared, cancels with the meter squared up there. So we're left with newtons. A very tiny number, 6 times 10 to the negative 8 newtons, or like 60 nanonewtons. Obviously, we don't really feel the force of gravity between people on an everyday basis. 290 kilogram students, that's about 200 pounds apiece. And they are about 10 feet apart, so they really don't feel the force of gravity from each other, but it is there. It's just really tiny. Next, we have a 35-gram ball, a 2-kilogram ball, and they are 5 centimeters apart. Really important. Convert to SI units. So that 35 grams has to become 0.035 kilograms. That 2 kilograms stays as 2 kilograms, and that distance has to become meters, so it's 0.05 meters. And G, write it down, put in the units. There we go. Now we don't have to put in units when we plug it in. Plug it all in, I get about 1.87 times 10 to the negative 5 newtons. Again, a really tiny number because think about just 2 little balls sitting on the desk. They don't really feel the force of gravity acting on each other or from each other. Old Regents question here. Calculate the force of gravity between the Earth and the Moon. So let's see, big G, write it down. Okay, that looks like a 4, but it's an 11. Okay, 11. Okay, write it down with units. Mass 1, mass of the first object, the Earth. Look it up on your reference table. Mass 2, mass of the second object, the Moon. Look it up in your reference table. The distance between them, not the radius of either planet. It's the distance between them, which is 3.84 times 10 to the 8th meters. Plug everything in there, and you should get about 2 times 10 to the 20 newtons, or like 1.99 times 10 to the 20 newtons. Work on that. Make sure you can get that answer in your calculator. If your calculator gives you this E, that means times 10 to the. So 2E20 means 2 times 10 to the 20 newtons. Now, I changed up this question a bit. In one of my classes, I said calculate the force of gravity between the Earth and the Sun, but you needed the mass of the Sun, which you had to look up and define the force of gravity, and the force of gravity you found was equal to what we found a few classes back. So I changed it in later classes. Now, this was a really good exercise because we hadn't solved for a mass yet. We'd only solved for the force of gravity. So this is a nice exercise to change it up. So if you were in my period 7-8 class, this is definitely good practice to try this question in a different way. So I wanted you to calculate the mass of the Sun. You know the force of gravity between the Earth and the Sun. We did it in class 44. Okay, we figured out the centripetal force acting on the Earth, which is the force of gravity that the Earth feels. 3.56 times 10 to the 22. So that's where we got the force of gravity. So that's Fg. We know the mass of the Earth. We know the distance between the Earth and the Sun. That's on the reference table. We know big G. Make sure all the units are there. Write our equation with nothing subbed in yet. Now just plug everything in. Fg, again, we know it from class 44. Plug it in. big G, mass of the Earth, mass of the Sun is m2. It doesn't matter which one's m1 and m2, and the distance between them is on your reference table. Don't forget to square it. You got to do some algebra here, okay? You got to like multiply both sides by 1.5 times 10 to the 11th squared. And you got to divide. So there's a bunch of steps. Make sure you can work through the steps. If you need help with that, let me know. And you should get that the mass of the Sun is equal to 1.99 times 10 to the 30 kilograms. And that is about the accepted value, 2 times 10 to the 30 kilograms. And just an important note here, you already know this, but just know that gravity is only an attractive force. It never repels.